So welcome to those who have decided to join us here today. My name is Rachel Martins. I am a research engagement strategist with CanChild and Kids Brain Health Network. And if you have any questions about today's event or anything that Kids Brain Health Network does, I'm going to put my email in the chat and you're welcome to connect with me as well. Now, the reason this whole event began, actually, it kind of goes alongside with the title, which is Luke's Legacy Family Research Rounds. Now, Luke's legacy is actually based on my son, who was born with mosaic trisomy 22. So he was quite a medically complex young man. And unfortunately, he passed away last year, a few weeks short of his 14th birthday. But he was a dynamic personality who demanded a seat at any table available to him when he decided that that was a necessary thing to do. And I thought that that was just such a wonderful thing when Kids Brain Health Network said, we would love to have him as a feature title for this research rounds project. And so I'm not going to encourage you today to engage with people in the same way that he did, which was pinching people if they weren't paying attention. But at the same time, I'm very honored to introduce you to someone who actually used to care for my young man and gotten to get to know over the years as well too, as a part of the same network with Kids Brain Health Network. And so I'd like to introduce you today to Dr. Adam Kirton, who works at Alberta Children's Hospital, and also as well to my partner, who is Dr. Kinga Posniak, who helped as my partner in crime here with this research rounds. There will be a live stream on Facebook for this on the CanChild Facebook page, if anybody has an interest in following there or needing to catch up or wanting to share that with a friend. And we will also have this as a podcast version on Spotify. So it's more accessible for families as well too. So it's a nice way to listen and learn on a drive. And we also carry this on the CanChild website under Luke's Legacy Research Rounds. So you can actually watch all of the prior videos if you miss anything. So we try to make sure that this information comes to you at the right time, in the right format where it's understandable for everybody. And one of the things that we really encourage here as well too, much like in any pediatric grand rounds, is that we consider everybody who attends as a fellow colleague. And so we create spaces for people to ask questions, to potentially make suggestions with projects, things like that. And so today, I'm going to just hand over the microphone to Dr. Kirton, and we will look forward to having a conversation afterwards.
Okay, great. Thank you, Rachel. Thanks for the introduction, and thanks to you and Kinga. Thank you for inviting me. It's a pleasure, first and foremost, to speak in an event named after Luke, and but also to participate in something that I think has been a long time coming, to see rounds organized by parents for parents in the research world is a great thing. And so I'm really happy to participate. It's also, I was trying to think how to present to this group tonight. And I think the message is that I used to think when I started, I've been doing this for a while, and I used to think we were pretty connected to parents. I used to think we were fairly patient-oriented and patient-centered, and it turns out we probably weren't. But we're getting better, and we're learning. And it's events like this that are teaching us in the clinical and research world, I think, how to do that. And so that's actually what I'm going to present today. I'm going to go through kind of a timeline of our research in Calgary and across the country, where we have certain areas of interest that I think will hopefully be relevant to most of this audience. But along the way, just try to show how we've tried to evolve and the lessons we've learned about how to really work with parents and patients and families as key partners in the research team, and hopefully that's fits with the philosophy of this event. And I think we've done some good things, but we've made tons of mistakes too. So I'm going to just admit to what those are, and I'd be very interested to hear from everybody at the end. And I should have left lots of time for questions. So I'll get started. And here we go. So I wanted to start with just a note about this sweet boy who, as Rachel said, I had the chance to know and care for quite a few years, and was so sad when we lost him. And I don't remember, he never pinched me, I don't think. I always remember him being really polite and cooperative, and I'm not sure he would always do exactly what I asked him to do, but it was always a pleasure to see Luke and his family in our clinic. And I can't think of a sweeter kid and family to have this event named after. So thanks for asking me to participate. So what I'm going to do is actually give you I'm going to show you a bunch of slides that I normally use for my presentations. I'm going to spare you the boring scientific talk. There's only a few graphs and I won't get into the details. But in the interest of real, patient and family participation in research, I'm going to make this, in a sense, a real, core research talk. This is the research that we do and that we're really excited about. But I'm going to try to present it and from a perspective of what might be perspectives of patients and families, why we did it, why we think it might matter to patients and families. And I'm happy to have people point out when I'm wrong and disagree with me if I'm missing the boat. But I'll try and show how we've grown and tried to improve the patient-centered focus of our research. And so a lot of this is how even if you were a bunch of boring neurologists and I was at a meeting somewhere, these are a lot of the same slides I would use. So hopefully you have learned a lot about the sort of scientific side of things at the same time. So I usually start with a picture like this, and this is an MRI scan of a newborn baby. It's a 1-day-old baby, and the baby seemed fine, had normal pregnancy, normal delivery, no complications, and then had a seizure on the first day. And that's why we saw them and did an MRI scan. And this type of MRI, this is the brain, and this is the front, this is the back. And on this type of MRI, bright is bad. So this entire bright area here, everything's flipped. This is actually the left side of the brain, is a big stroke. So this is a blockage of a major artery in the brain. And the bright signal means all these brain cells are dying, and there are billions and billions of brain cells in here. And this is a big brain injury. If you or I had this stroke, we would be probably devastated in many ways. And this baby's going to grow up. They will survive, and they'll have difficulty. They're going to have weakness on one side of the body. That's a form of cerebral palsy. And they may run into some other challenges in development. But they may also do really well. They may do a million great things in their life, and how they can do that after such a big brain injury when us old people would be very disabled by this is a real mystery that we're interested in. And one of the messages of today is, at least for stroke, this is called perinatal stroke, where it's one injury on one side of the brain. A lot of it has to do with all this healthy brain on the other side. All this light gray brain here is pristine, totally healthy, young brain right at the beginning of life. And it has an amazing capacity to develop around an injury like this. And the degree to which it can do that, we think, plays a big role in how well kids do as they grow up. And so we're trying to study that, and I'll show you a bit about how we do that to understand how some kids do very well, some don't do as well, and why those differences might be. And so I'll tell you some real patient stories. This is Alana, who was, at the time of this picture, I think it was about 13 when she first came to our program, and she had a stroke similar to the MRI I just showed you around the time she was born. She had cerebral palsy on one side. She had some other challenges in her brain health. But her goal in life was to become a ski racer. She loved to ski and still does, I'm sure. And this is her now as a young adult, and she can ski. She is a world-class Paralympian skier. She's won medals, and for Canada, she's top ranked in multiple events. And so she had a brain injury, like I just showed you, and now she's this world-class athlete, which is just remarkable. And now she's an outlier. Of course, most young people, whether they've had a stroke or not, don't perform at this kind of level. But she's a testament to the power of the developing brain and its plasticity and how it can develop. And so understanding how that can be is really what a lot of our research is about. So on the research side of things, these are the kinds of learning objectives that I'll give you a feel for, a bit to understand a bit about perinatal stroke and why it's such a good model of injury in the developing brain, we think. Next, a bit about how the brain develops. We call that developmental plasticity. How does that happen, and how does that determine long-term outcomes? And then lastly, how do we take that knowledge and turn it into not just treatment, but really trying to think in a patient-centered way about not just trying to fix a neurological problem that we can see, but to think about how kids can participate and achieve their goals like Alana did. So I'll give you a little bit of a primer about perinatal stroke. I don't have any significant disclosures. The things I'm going to talk about, the brain stimulation and some technologies, it's all still experimental. So I'm not making any recommendations for treatment. So this all started about 15 years ago when I moved back to Calgary, and this is Alberta, I'm sure everybody knows. The reason I'm highlighting it here is that we've really been focused on perinatal stroke. And this is Mri Dunbar, who's just finished a fellowship with us. She's a pediatric neurologist and joining us on the faculty here. She just published this paper. It took us these 15 years to analyze this data. But what we did when I first moved back to Alberta is we tried to connect with every family that had a child who'd been affected by perinatal stroke. And that took 15 years and lots of looking through charts and medical record searches. And then from the patient perspective, which I'm going to try to focus on tonight, what it also included was we had to actually reach out to families who maybe had never even known that their child had had a stroke. They just had been told that they had cerebral palsy. They didn't know why. And we would invite them we started these research clinics at the Children's Hospital. And we said, we have a new program. Would you like to come? We can't fix the stroke, of course, but we might be able to suggest some new treatments, give you some more information, explain a bit more about what might have happened. And the response from families was amazing. So we had a very high recruitment rate. We think we've probably captured about 95% of the families, which adds up to over 1,000 families in Alberta. And I started with this because this was how the whole program started, but it's also really the core of what our program is about. It's really based on the willingness of families to participate, to share information, and participate in research. And everything I'm going to show you, we wouldn't have learned any of it if we hadn't started by reaching out and having families be willing to participate. And so I wanted to start with that very important acknowledgement. And what this has shown in this particular study by Mri shows the incidence is about 1 in 1,000 live births. It's actually much more common than was previously reported. That adds up to about 10,000 Canadian children who are currently living with perinatal stroke. So it's not a small problem. And we don't have to get into the details, but a stroke really means a focal vascular brain injury. And it turns out what I'm showing here, there's actually 5 or 6 different kinds. It depends a bit about, was it an artery or a vein that got blocked? Did it get blocked or did it burst? That's called a hemorrhage. Some strokes only occur in the fetus, some occur closer to birth. And we use MRI and other things to sort of subclassify the strokes. But what they all have in common, and what this cartoon that Mri made here is showing, is there's different ways a stroke can injure the brain. But for the most part, what they have in common is that they're all a focal injury. Like I showed you on that first MRI, one injury, usually just on one side of the brain. And that's why it's such an informative model of how young brains develop after an injury. The names aren't too important. Sorry, it's a bit complicated, but I'll walk you through. This is why we think most of these strokes happen, at least the ones that block an artery. And because everybody always asks, why would a baby have a stroke? The vast majority, not always, there are other reasons perhaps, but the most common reason is probably a problem in the placenta. So the placenta gets sick. There are different ways that can happen. Usually you can't tell, the mom doesn't know, there's no way that her doctor can't tell, but some clots might form in the placenta. And most of you, I'm sure, know that the placenta is the main source of oxygen and nutrition, of course, to the baby, but it's connected by blood vessels through the umbilical cord. So if a clot leaves the placenta and enters the baby's circulation, it goes up to the heart and then it gets pumped out, and most of the blood goes to the brain in the fetus. So the clot goes up into the brain and it blocks an artery and it creates a stroke, sometimes just on one side of the brain. It reminds you of that first picture I showed you. Sometimes there's two clots and you can see a stroke on the other side of the brain. And obviously that's an even bigger problem. But this is probably explains most of these are called ischemic strokes. That's a lack of blood flow or a blockage. This probably explains most of these injuries. The only good news there is that these strokes virtually never recur because, of course, you're only attached to the placenta until you're born. As soon as you're born, the risk factor goes away. So they virtually never happen again. This is a study, and again, don't worry about the graphs. Sorry, don't worry about the numbers. The point is, again, families participating agreed to let us sample the baby's blood spots. So everybody probably remembers that your baby gets a blood spot when they're born. And these actually get stored. And so we got permission to go back and analyze this blood for a whole list of, they're called cytokines, but a whole list of factors that float around in the blood and actually are still there up to 7 or 10 years later. And we compared it between babies with stroke and babies who hadn't had stroke. And what this colorful blobs are showing is that we were actually able to distinguish just on these things floating in the blood, babies who were high risk for stroke versus those who weren't. And it's very exciting. And but I also mention it because even though we have these sort of markers in the blood, we still, remember I said it's about 1 in 1,000 births. So we still, even if we gave this test to every mom at say 38 weeks of pregnancy, we might get a hint, but we still wouldn't know who's going to be the 1 in 1,000 where their baby might have a stroke. And that's a bit discouraging because even though we have some hints in the blood, we still don't have a test. We still don't have a way to anticipate or prevent these strokes from happening. That would be ideal. And to be frank, I don't think we'll likely ever have a way to prevent these strokes from happening. It turns out there's nothing you can do. There's nothing, and I'll get to that in a minute. And that's why a lot of our work is focused on rehabilitation and outcome because we can't stop the strokes from happening. There's another test, and part of this is to show you how boring neurologists are. We like to put up graphs and numbers and things. Those aren't important. What's important is the message. And so from a family perspective, this was a study we did. Colleen, who was one of my residents at the time, we used to worry about, because it's a blood clot, we used to worry that maybe these children had long-term blood clotting problems. Did we have to worry about them forming another blood clot later in life? And so we did this big study, not because we actually really thought it was going to tell us why strokes happen. It was because when we talked to families in the clinic, they were worried about this. And so were doctors. We didn't actually know the answer. So we're like, gee, I hope she doesn't get another blood clot, and maybe we should do some tests. And then we started doing all these tests, and then you would get back results and you weren't sure. It led to a lot of anxiety, a lot of angst on the part of the family. And so we actually did this, I would say, in a combined way. We had a scientific question, but we also had a real a question that was relevant to families. And the good news is we found out in this big study that there's actually really no increased risk long-term for blood clotting disorders. And we've actually stopped doing all of these blood tests on these older children. And so we don't worry about it. The families don't worry about it. The kids don't need unnecessary blood tests. And so sometimes those questions that really matter, what might be a simple question from a family point of view that we just don't have the answer to, that's a good reason to invest what took several years and a bunch of money to do a well-constructed study that really answered the question. And it's let us move on and improve the care of patients in the clinic. This is another MRI scan. It shows a different kind of stroke. This is the brain looking straight on. And you notice the brain actually looks pretty intact. There's just this one little area of damage here. And unfortunately, this is right where the motor pathways run. So this is a smaller stroke that occurs in the fetus. I won't get into the details, This is actually a fetus that hasn't been born. This is a fetal MRI scan of this same stroke happening. And so it damages just the motor pathways, and same basic outcome leads to a cerebral palsy, that is a weakness on one side of the body. And so I mention it because here's another famous patient of ours, Mike, who's also now a young adult. He had, that was what his MRI looked like. He had that stroke. He had a weakness on one side, wanted to be a bike racer and couldn't change a flat tire on his bike because his hand didn't work very well. But he came to the program and did a lot of hard work, and he learned to change the tire, and he really learned how to ride a bike. And you can see him here. This was in Rio, where he won a bronze medal for Canada in the Paralympics. And he's since been, he was on the Youth Advisory Committee for Child Bright, and has participated in many events here in Calgary, and been an advocate for youth with perinatal stroke and CP. And so another great example of what these young plastic brains can do. The other big type of perinatal stroke is a hemorrhage. So this is a breakage of a blood vessel rather than a blockage. And we did a big study about hemorrhagic stroke a number of years ago that's published here. These are all, there are many different reasons why the brain, a newborn's brain might have a hemorrhage. These are just some pictures showing different types and locations. The basic messages are the same, that these happen for a variety of reasons that we only partially understand. They have a very low recurrence rate, which is good news, and a high capacity for recovery. The important thing there, again, trying to think to the family perspective, is why did this happen, and to make sure people don't have any misplaced feelings of why it might have happened. The most common, when we see hemorrhage, most people think about trauma, and for a long time people said, well, the birth must have been traumatic. There's all sorts of amazing research now. This is a study from France of babies actually being born in the MRI scanner. These are just 3 examples. These are 3 babies. This is them before the second stage of labor, and this is during the second stage. And it's showing, literally measuring the incredible mechanical forces that happen. These are normal children, normal pregnancy, normal delivery. The mechanical forces that happen in pregnancy, which are often quite dramatic, but this is a normal part of being born. But because of that issue, and again, sorry for all the pictures and graphs here, the point is, it's all in the title. We did an MRI-based study to actually measure signs of trauma on the outside of the head as an estimate in healthy babies and babies with stroke and other types of neonatal brain injury. And we're just about to publish this, and it showed that there's actually no association with the amount of force or the signs of trauma. It's intuitive, makes good sense. And if a baby comes out bruised or has molding, it's called, right, misshapen head, and then we also find out they have a brain injury, it's very logical to put the two together. But the science is now telling us that that's really not, almost never is that the case, and which is important. I think very important for parents to understand that sometimes what you see, or might think what you see on the outside, explains what's happening on the inside. That's not always the case. So another kind of, I think this was very much a parent and patient driven research question that we asked, because we heard it all the time. They were like, the delivery was so difficult and she's so bruised, and now you tell me she has a brain injury, they must be related. And totally understandable, but important to know the truth. And I think this is my last note about perinatal stroke. This is a positive new direction. It's called the Dinosaur Trial. This is a clinical trial that we're participating in. The other question we would get from families after we might tell a family in the NICU, your baby's had a stroke. And here's that MRI. It looks just like the first one I showed you. This is a new, fresh stroke that's just happened. One of the very first questions from parents is like, well, can't we do anything to help the brain recover or be less injured? And up until this clinical trial started, we wouldn't have very good answers. And this sweet little girl was the first child outside of Holland, which is where the trial was initiated from. She was born in Calgary, and we've since enrolled 3 children in this trial. It's a hormone in our bodies called erythropoietin. The details aren't important, but it's being used in a variety of neuroprotective trials, that is, protect the brain after it's been freshly injured, help it recover. And it's been tried in a variety of forms of neonatal brain injury and now in neonatal stroke. And so it's very exciting. We don't know yet even if it works or how well it works, but to have an opportunity, and that again, it comes from a question from the families, and it needs the trust and the investment of the families. I've approached, I or our team have approached 4 families, and we've had 3 consent. Another family chose not to after lots of discussion and the informed consent process, and made their own informed decision. And so it's very hard. It's a very stressful circumstance, and so we try to learn. We try to connect with the family, understand their hopes, their worries, as part of that informed consent, and we're learning with each family that we encounter in this trial. And so this is a very important note, very much from the family perspective, and this is as we learned, as we built up this big cohort, and we got to know more and more families, a common theme emerged around why did this happen. We didn't have great answers, and so it became clear that a lot of parents, in particular moms, were worried that we couldn't tell them exactly why, and so therefore it must have been something else. I must have done something wrong. There's so many rules of pregnancy I read on the internet. Did I eat too much of this or not enough of that? Or did I not exercise enough? And none of which, we have lots of evidence, none of that causes neonatal stroke. We know that, but we never got that message out and used the evidence to alleviate these misplaced concerns. And so we did it. We developed a measure for this. We had, again, lots of participation from families who were willing to tell us what their thoughts were, what their worries were, what the long-term outcomes were for themselves, their mental health, their family. And we published a variety of studies on this that show that things like misplaced guilt or blame were very common emotions, and which is really tragic because it should be quite preventable if we just got better at informing families about what the facts are and alleviated those fears. And so we started developing some tools to do that seem to be working. These are some screenshots. I probably won't have time to play the video for you, but I'll just show you. And we do a lot of this work through the Heart and Stroke Foundation, who've been a big community supporter. I'll show you the first just couple of seconds here. We made this whiteboard video.
Most people are surprised to learn that babies have strokes.
You guys can hear the...
In fact, the most focused period of risk for stroke is the first week of life. Perinatal stroke is a focal vascular brain injury occurring in the fetus or newborn. Perinatal stroke is the leading cause of hemiparesis when a blood vessel in the brain, why an individual child suffers a perinatal stroke. Many strokes near birth result from a problem in the placenta, the physical connection between a mother and her baby.
So I won't play the whole video just for the interest of time. And whoops, sorry. But you've probably seen whiteboard videos like that. It's available. I'll give you our website at the end. It's
most people are
available on the front page of the website. And we're actually participating in a study with friends in Boston and elsewhere to look at the effectiveness of this intervention on parental mental health. And we had a lot of patient input to design the video and feedback, and which was extremely helpful. So that it took us about, I'd like to say 5, it was probably closer to 10 years to realize what an obvious problem this was and then do something about it, which is in hindsight seems way too slow. But again, it really came from trying to see things from the side of parents and listening to parents, which we thought we were doing, but maybe we were too slow. So I'll move on to the next part, which is, it gets a little more scientific about how does the brain recover after perinatal stroke, and how would we ever figure that out with working with real children and their families. This is the way we look at development. So from left to right, here's birth, and here's, let's say 18 over here. And we all go through some developmental curve. We all have our own curve. And development is very fast when you're little and everything slows down. And we all know here it's all downhill after 25. And so if you have an injury at the beginning of life, like a stroke, how's your developmental curve going to be different? Well, I've shown you some examples. Some kids have some difficulty, but they succeed amazingly well. You could think of that, is that a good stroke? And other kids are less fortunate, and they run into bigger problems, bigger hurdles, and their development is more impaired, and they don't do as well. Or some even start off well and then run into problems midway. That's perhaps even worse. And so what we're trying to figure out are what are the factors that push kids up or down these developmental curves? How could we nudge kids a little bit on a steeper curve down here so that they end up with a better outcome over here? And there are many factors, we think. Most of them are not well understood, and I won't get into most of them today. But we're certainly very interested in these positive factors up here, like therapy, which of course we do lots of work in that area. Can we enhance therapy with neuromodulation? I'll tell you what that means. Life experience. How do we turn on brain plasticity? Many factors, only some of which we're starting to understand. And so the outcomes from perinatal stroke, here's Mike again when he was only like 13, and this is his therapist. This was some exercise they were doing in our program. He's focused on his motor system, like I mentioned, so hemiparetic or unilateral cerebral palsies. That's the most common problem after perinatal stroke, so we tend to focus there. Only about 1 in 3 children will run into more complex deficits, things like learning, cognition, behavior, and things like epilepsy. There are some reasons we're kind of understanding for that, but they're hard to predict. And so a lot of what I'll show you focuses on the motor. We spend time on these other issues, but I won't get into that today. And so how does the brain develop after an injury? And we try to build these models. That's what this slide is showing. This is a simplified cartoon of the motor system. And I won't get into the anatomy too much, but usually this is the brain up here, and it sends projections down to your spinal cord, which looks like this, obviously not in proportion. And it sends nerves out to, let's say, move your hand, usually on the opposite side of your body, right? So for most of us, our left motor cortex, that's LMC, crosses over and controls the right hand. But when you're born, you actually have connections from both sides of the brain down to the spinal cord, actually about even 50-50. And so if you have a stroke early in life on this side, what some kids' brains do as they grow up is they actually maintain these, what we call ipsilateral connections. So the right brain is in part controlling the right hand. And normally these connections are there, but they just die away in the first few years of life. But sometimes after a stroke, you'll maintain these, which sounds like a good idea. You could use a different pathway to control the hand. Turns out when you do that, it actually doesn't work very well. So, but this is a kind of cartoon that just to give an idea of how we think about the brain and how it might develop. And this is intending only to show you a lot of pretty pictures, that there are many ways to use MRI scans, which is one of our main research tools, to take pictures of young brains that have had strokes and figure out what are they doing, how are they organizing themselves. And there's all these different types of MRI pictures that we take, and each one gives us a different piece of information about this area or this pathway or how they might be connected. And that's what all these pictures are showing. And the tools are amazing, better than they've ever been. And so we do lots of MRI research to figure that out. And I won't bore you with that detail, but here's some other pretty pictures. So we're not just interested in the motor pathways. This is the cerebellum, which is involved in mostly in balance at the back of the brain. We know they're connected. We can actually measure those connections. We can measure the size of different pieces of the brain, like the thalamus shown in this picture. And this is work from Brandon Craig, who just finished his PhD with us. He's now a medical student at U of C. He took on this new way to use what's called diffusion imaging. And instead of just picking one spot or one pathway, we can actually image the whole brain and try to look at the whole connectivity, we call it, or connectome, of how all the white matter, all the pathways in the brain are connecting to each other. And as you can imagine, that gets pretty complicated pretty quickly. But that's what these pictures are showing. Beautiful pictures to look at. And what Brandon published this beautiful paper in Neurology, it was on the cover of Neurology just about a year ago. And again, sorry, too many graphs here, but what it shows is this really strong connection, not just on the stroke side of the brain, but on the other side. Remember on the first slide, I showed you how the healthy side of the brain is probably really important. this showed that the healthy side of the brain is completely different in kids who've had a stroke, that it's really affected the development of both sides of the brain. And how that side is organized is really important in determining their function. That's what these graphs are showing. So really exciting progress, just how we can use sort of a cutting edge tool to do that. And so that lets us build not just the one cartoon I showed you, but some new fancier models of how the brain organizes. And again, trying to come back to the family perspective, why would you care? Well, what we really like to do, we can look for patterns across groups of children, but what most families care about is their child. And so can we use this to create a personalized approach to understanding the brain and maybe how to help it function better? We're getting there. We're not there yet, but this study I'm citing at the bottom here from Helen Carlson, who runs my imaging program, she used machine learning and some fancy technology with all this data together. And we're trying to build what she calls a dashboard, where we would actually have such a good understanding of all the patterns that then when we meet an individual child, we could place them onto this dashboard and say, okay, the way your brain organized, over here you did this, over here you did that. And we're learning where you fit in the grand scheme of things as an individual. If we can get to that, then maybe we can start to learn about, okay, now we're not just going to prescribe the generic therapy for you. We've learned that when you're over on that side of the spectrum, you'll do better with this therapy instead of that therapy, for example. So we're not there yet, but this is a key step for us to get towards more personalized medicine in perinatal stroke rehab. And the other tool we use to map the brain is called brain stimulation, or one version is called transcranial magnetic stimulation. So we give little magnetic pulses in a special machine, and we measure the response of, in this case, it's the motor system. You can see it's pretty painless, pretty fun. This is Aiden, is one of our, he's now 19, I think. It's hard to believe. And but a very neat tool that lets us map the brain. And sorry, just ignore the graph, but there's a version of that cartoon I showed you. Remember how I said you can have connections to the other side, but also on the same side? This is the TMS coil, we call it. If we give a little magnetic stimulation on one side of the brain and we get a response in both hands, we measure the muscles on both sides, we can use TMS right there to tell us, oh, you're a person who's kept your ipsilateral projections. This is how part of how your brain is wired. And it turns out that simple experiment tells us quite a bit about how the kids might function in their motor system. So again, it helps us build personalized models. Again, we learn more from individual patients and families. This is a young boy you'll see here.
Starting with that hand.
Has mirror movements, which some of you might be familiar with. I'm asking him just to tap his left hand, but if you watch, when I get him to do it, you see his right hand actually does a similar version of the movement, and he can't help that. And he had a stroke around birth, and that actually has to do with this cartoon. It has to do with why, because one side of his brain has in some control over both hands. That's why they move together. So we're hoping someday, instead of fancy MRI scans and brain stimulation to map out how the brain developed, if we understand it well enough, we could just have them in the clinic and say, okay, do this, and be like, oh, okay, now I understand how your brain developed.
Perfect. Good job.
You should go to have this kind of therapy. Still not there yet, but coming back to individual patients to try to understand how their brains have developed. And the tools get, as I said, with MRI, they just get better and better. This is a TMS robot we have in the lab now. So instead of, I used to do this by hand, but now the robot can actually go around. This is the TMS coil, it's called. And we can navigate it onto the patient's own brain MRI scan and have it go around and give stimulations and measure responses. And this is a representation of just one muscle in his hand on one side. And so the TMS technology is getting really good. And we have other technologies. This is called the kin-arm robot that kids can sit in and do tasks with both their limbs, and we can understand not just how they move, but how they sense their limb and how they sense the movement of their limb. We've done a variety of studies in that area, and it gives us just one more piece of the puzzle. And it might even be a therapeutic tool. This beautiful young lady who's the champion child for the Children's Hospital this year had a big stroke a few years ago, and she actually participated, came in, used the kin-arm robot. And that, again, that's that is very patient driven. Sydney, you know, was this motivated teenager, and she said, I want to try everything. I want to get better. And so we had this opportunity and we tried, and she's now doing terrifically well. Okay, last part, and I want to leave time for questions. So I'll go quickly through this last part. So hopefully now you've got an idea. So what is a stroke? Unilateral injury. Brain develops around a stroke. We can get an idea of that and how it determines function. That's all very interesting. But to be patient-centered again, I could, if I would see families in clinic and tell them all this and could say, well, we're doing some research and I can tell you that the corticospinal tract on that side of the brain is doing this, you might say, well, thank you, that's very interesting, but what can that do for us? You know, how can that help my son or daughter participate more in things they want to do, right? And for a while there, we didn't have any really good answers. But that really is what motivated us to try to translate the knowledge and push this incomplete but emerging understanding of things into interventions. I'm going to show you two approaches to how we do that. One specific to stroke and one a bit more general. So here's that graph again of development from birth to adulthood. Remember I said, what might we be able to do to push kids up these curves? And therapy probably works. That turns on natural plasticity in the brain, but it's slow. You need a lot of therapy usually to make a little change. What if we could enhance the plasticity so that when their brain's trying to change, it could change better, change faster, or maybe with less effort? And that's where this idea of therapeutic brain stimulation comes in. So as opposed to giving magnetic pulses like I showed you for TMS before, one at a time, you give them repeatedly. That's what this boy is doing here during one of our programs. And it can actually, over minutes, can actually change what we call the excitability of, in this case, the motor cortex, or the main movement control center in the brain. And you can't just do that. You have to pair it with therapy. So here's Alana, who I introduced you to. She would do brain stimulation and then go and do therapy. She's doing constraint therapy here, which people have probably heard of. She's wearing a cast. This is her good arm. And while she's working her weak side, doing some video games and other types of therapy. So we did this trial called Plastic Champs, where we combined brain stimulation and therapy, very intense, 2 weeks, all day, every day. That's what's shown in this cartoon here. Kids would come in all day, every day for 2 weeks in a row. We would measure their brains and their function very carefully before, and then we would measure it over and over again up to 6 months after the intervention. This was 45 kids. And the camp models were, I think, this is one of the earlier things I think our team gets big credit for. We were very patient-centered. The kids and the families helped us design, along with child life specialists and occupational therapists, these full-day camp models that had to be, you know, kids weren't going to sit at a desk and practice doing exercises for all day. It had to be fun, had to be engaging. And so they did all sorts of things, sports, games, as rock band, cooking, all sorts of fun things to work those muscles, work their brains towards the goals that they set. And I said I wasn't going to show too many graphs. This is how we measure their satisfaction and performance with the goals that they set. These are all 45 kids together. These are called box plots. Don't worry the details. Up is good. Their scores improved from about an average of 3 to an average of about 8. This is how they feel about their achievement of the goals that they set before the camp started. And so it's a less scientific measure, but it comes from the patient perspective. So we put a lot of stock in it. And at the very least, even the camp only lasted 2 weeks, but 6 months later, their scores were actually still going up. So maybe because they were participating more, we don't actually know. But an important patient-centered measure that maybe this was doing something. And without getting in the details, this is a more objective measure, and this is by treatment group. And what we found was that if you didn't just do therapy, but you added on constraint therapy and brain stimulation, the group who got both, this was a randomized trial, the group who got both did better. They were more likely to achieve a higher change in this outcome measure. This doesn't prove that brain stimulation works, but it was an early step in that direction that helped us move forward. And this I included from the Plastic Champs trial because this was our wrap-up event, which we had. And this is only about half the participants that could make it. We did it at the end of the trial, just to give you an idea of how what a big team it is and how patient and family oriented it is. Most of the people in this picture are participants or their parents and siblings. The rest of our team is scattered in there. Here's a younger me at the back here. And so the families really made this program. This is a big clinical trial, but it was really the families that made it happen. And their participation was really meant everything. And so we've tried other forms of brain stimulation. This one's called transcranial direct current stimulation. It's a different approach. It's very tiny bits of electrical current instead of magnetic stimulation. And we've shown in this study that if you do that, we've done studies in normal children, typically developing children, to prove the principle that this kind of brain stimulation can help you learn a motor task with your hand. That's what this graph is showing. That had been shown in adults in the past, but we thought it was important to show it in children as well. And so we took that approach again to kids with perinatal stroke and cerebral palsy. Here's some kids. This is an after-school program. You can see they've got, these are TDCS sponges on their head. They can actually do it while they're doing therapy. You can see in that picture there. And that trial, well, that was a smaller trial, looks like it was positive. So it led to what's called the SPORT trial, which is funded through ChildBright. We were supposed to finish 2 years ago. We were almost done, but we couldn't do our last summer camps because of COVID the last 2 years. We will finish next year. There'll be almost 100 kids in this trial. So in our world, it's a big trial. This was from the first summer. This is all the kids in the camp, tug of war against our research team. And you don't have to guess who won. It wasn't us. And so really looking forward. So stay tuned for the results of that. And so we don't have any of the objective outcome measures, but we have awesome patient-centered outcome measures like this one. This was a spontaneous text from Brandon and his mom, I think a few days into the camp. And he just said, wow, he said, I think my hand works better. I can move my thumb. And very small and, to look at, but for him, it obviously really meant something, and talked my ear off the whole way home. He wants the camp to last for a month. And so this is a great outcome. Like that counts. I don't care what the statistics say. If we get outcomes like that, we're very happy. Okay, I'm going to just skip that in the interest of time. Okay, last point. I'll just take 5 minutes to tell you about a new direction we've gone that where I think we've gone to a better, higher level of patient engagement. And so I showed you this stroke. This is an MRI of another patient I follow who also had perinatal stroke. And at first glance, her MRI actually probably looks a bit better, not one big stroke, but she had 2 strokes, and they're not even big. They're actually very small, but they're right where those 2 motor pathways run. And so instead of just having CP on one side of her body, she's hit both sides, which is just a horribly bad luck for her. And so she has a different kind of cerebral palsy that is much more severe. She has quadriplegic cerebral palsy, which I think most people are familiar with, but all 4 limbs. And in this case, there's a wide spectrum of kids with quadriplegic CP. There are different subtypes that people may be familiar with, but there are some young people, like perhaps this young man, who you can see have very severe motor dysfunction, can't use their hands, can't walk, and usually can't talk, but may have a very high cognitive capacity and awareness. You can see just looking in this young man's eyes, you can see how bright and engaged he is. Some children are intellectually normal or even gifted, but there's a large separation between their cognitive and intellectual capacity and awareness and their physical disability, which is very severe. And so this is analogous to what in adults is often called a locked-in syndrome or a trap syndrome. And it's very, very difficult and a very challenging life for such children and their families. And without really a lot of options of ways to help. There are many efforts made and lots of things we can do to help, but in terms of actual participation in life, it's very difficult for many of these children to participate. And so that's what brought us into the world of brain-computer interfaces, which I'm going to give you a quick synopsis of to finish. If people probably haven't heard of this, it's a bit of a difficult concept, so don't worry if you don't get it right away. I'll send you to our website and you can learn more. But a BCI or brain-computer interface has 3 components if you look at this cartoon on the right. first, you need to sense brain activity. And we can do that quite easily. You can put on an EEG, some stickers, and you can measure brain activity continuously. You send that information to a very smart computer that looks at it and says, okay, I see all these brain waves. And it says, okay, this is subject, A, and this is what his brainwaves look like. And then you tell the subject to do something specific, a specific thought, like think about opening and closing your left hand. And if you or I do that, it actually produces a very predictable change in your brainwaves. And if you tell the computer and you say, oh, okay, for the last 10 seconds, he was thinking about his left hand, the computer can look and say, oh, okay, I see the difference. I see before he wasn't, then he was. And now that computer can detect anytime you think about your left hand. And if that's true, then you could tell that computer, okay, the next time you see me think about my left hand, I want you to do this. And you tell the computer to go and control something, a wheelchair, an arm, maybe a computer cursor, just like I'm doing. Think about the left hand and move the cursor to the left. So this is a way that you can use your intentional thoughts to control something. And as I'm sure you've all surmised, if you're a person whose body has a great difficulty moving and you can't use your body to impact the world that you want to with your brain, the BCI is a potential bypass, potential solution to that. And that's why it might be a way to help kids with the most severe, particularly the most quadriplegic cerebral palsy. And so BCIs are not that new. They've been around for several decades. These are implantable BCIs only in adult patients. These ones are actually implanted in the brain. This is more invasive. But using such technology, paralyzed adult patients have been able to control robotic arms, control communication devices, computers, et cetera, and do quite remarkable things. This is the cutting edge of BCI technology. This is from, I was on the phone with these guys today. This is from San Francisco, a group last year. This is sensing a person's intended speech from their brain and turning it into speech with the computer. This is the same study. These are both published in Nature. In detecting a person's intended handwriting. This is the computer writing letters that the user is thinking about. It's amazing. This is Elon Musk's company, Neuralink, which promises very soon to have implantable, much greater sensors that will allow perhaps a much higher level of brain-computer interface. This monkey here is playing Pong just by thinking about moving the paddle up and down. So this is reality. This is not science fiction. The problem is all of this technology is rapidly advancing, but children have been completely left out of the equation for some fair scientific reasons, but what's ignoring what we think is a real moral imperative. And this is the United Nations Convention on the Rights of Persons with Disabilities, which you may or may not be familiar with. But if you read this with an eye to children with disabilities, there's a compelling argument that we need to be availing these emerging technologies to help kids with disabilities. And we certainly agree with that. And so we've started exploring the possibility of brain-computer interfaces for children. It's very early, but there's some encouraging results happening. If you still don't believe that it works, this is my son a few years ago. He's wearing a very cheap BCI. You can buy this on the internet. And with a little engineering, this is Bluetooth to a computer that you can't see. And the computer's Bluetooth to this car. And he was trained for about 10 minutes to think about pushing the car forward. We learned his brainwaves. And when we asked him to, he was able to drive the car and then stop it on the square. And he got it. And we did I'd like to say it was just my own son who was so smart, but he's the same as every other kid. We did a study with about 26 kids, school-age kids, and they were all good at it. They performed very similar to adults. So it's possible. And so this is where I think we took up our patient engagement to a higher level. We still have things to learn, but we went right away to families who had severe quadriplegic CP, like I mentioned. And we said, we think BCI might be able to allow your kids to do something more than they can do now, some way that they might want to participate, engage, interact with the world. Do you want to try? Do you want to come and help us figure this out? And we made no promises. Obviously, there's a lot of hope there, and we are very careful to say this may not work. The main risk is disappointment if you're willing to take that on. And the families, of course, engaged right away and have been amazing. And these are just some snapshots from our clinical program that we started a few years ago. And we're not trying to invent the next BCI. We're trying to take the technology that's quickly developing and put it in the hands and the hands of families that could stand to benefit from it. And these are just some snapshots. You can see this young boy who can't move is able to race cars with his sister. This young lady's using a spelling board to spell words. These kids are in the ICU. We actually took it into our acute care setting. This young boy's playing video games. This young lady, Peyton, who was the MRI I showed you at the beginning, is making artwork, and so is John here with BCI. And so quite simple things, but they work. And so one of my last slides, I'm going to show you. This was actually, I think, 7 families. I wanted to show you the whole video, but it takes up too much time, so I'll just show you the one. This is John. The families made these videos for an event that we had not long ago, and they chose the music. They did the whole thing themselves. So I'm just going to play you. So John's cute little sister kind of tries to steal the camera there, but otherwise just a fabulous family, and I'm glad you could hear from them directly. These are other kids in the program. Nick here racing his brothers. This is him playing video games, his brother watching. It used to be the other way at home. His brothers would play video games and all he could do was sit there and watch, and now it's the other way around, which is great. This is a new program that we call Power Mobility. So this is linking the BCI to this. It's called a Turtle Trainer. It's a power mobility trainer. We have a grant submitted at Kids Brain Health. If anybody knows anybody who wants to put in the good word, they're just deciding right now. But watch Daniel's face here. This is the first time he ever gets it to go. He's thinking the right thought, and there it goes. I think that smile speaks 1,000 words, and it's obviously still pretty crude, but he can do it. This is Matei, who I've known since he was born. He's going to almost run his mom over here, which she's pretty thrilled about. Signal is choppy and it's hard for him. He doesn't have perfect control yet, but he can make it move. And the big smiles on their faces are definitely a good early outcome that we're really excited about. So more to come on that. We've actually been doing home BCI. We have systems that we can use at home. Thanks to COVID, we were sort of forced to do that, but that's starting to work. And I think this is my last slide. This is just really, again, about the family engagement and how great the families have been. Ilias here is Daniel's father, is actually an engineer himself and is now part of our BCI team of engineers. This was an online family event we had last year. And the game jam, which just finished up, believe it or not, this was the families participated, told a bunch of game developers what they want BCI games to do. And on a weekend sort of hackathon, these game developers developed games specifically designed for BCI, the results of which will be out soon. The kids are the judges for the competition. They decide who made the best game. And there's a big prize. They get a BCI system and some cash. And so it's very exciting to see what's happening there. And this is really where we're going into this sort of customized, we call it through design thinking, a way to have patients and families set their goals, and then we try to match the goal with a BCI solution. This is complicated. It's not quite there yet, but it's what we're working towards. Okay, I've used up almost all my time, so I'm going to stop there. This is Peyton, who I showed you the MRI. This is some of her artwork that she won a prize for recently at our Brain Institute. And against those smiles that I think are the outcomes that we're after. So thanks to my research team, most of whom are shown here, and our funding. And if you want to know more about what I talked about, the BCI site is bciforkids.com, and we're on social media as well. Perinatalstroke.com has all this information about perinatal stroke and brain stimulation. And I'll put up a last slide that just has a qualitative study that's about to be published. I think the preprint is online if you're interested. These are quotes from the first families participating in BCI, and I think they say a lot from the family perspective. So I'll leave those up. You can read them while we're chatting. And thanks for letting me run a little bit long, and happy to take questions. Thank you.
Thank you so much for this amazing presentation. And it gets me thinking so much about Canchild's F words and how much fun family friends all kind of played a role in today's conversation. We ended up with a few questions for you today. The first one is, have you had experiences with identical twins who have had perinatal stroke?
I have had a couple of families in different ways. Twin pregnancies are probably, there's a slightly increased risk, it seems, probably for a couple of different reasons. And then it depends which type of stroke. There are also some rare genetic conditions that can predispose kids to perinatal stroke. So we do follow a couple of families. The vast majority are singleton pregnancies, and perinatal stroke tends not to run in families, but there are some exceptions to that.
Okie dokie. I'm before the next question, I'm just going to get you to stop screen sharing as well too. That way we can interact a little bit more.
Oh, okay.
All righty. So the next question is, with the study on brain stimulation, did you find any improvements in social communication skills in the participants?
Yeah, thanks. Good question. The approach, I probably wasn't specific enough. The approach in brain stimulation is we have to try to pick, the idea is to stimulate a particular target in the brain. And so that was the reason that we did all the imaging and the other things, to have a model of sort of where has function moved to, which areas are most important. And we focused on the motor system because that's where the most common difficulties are. And we have a fairly good idea of where the motor system has moved to. And so that's the part that we stimulate and train at the same time to try to improve motor function. They all kind of have to go together. You need the therapy, the stimulation, and the location. So for more complex things like language or social, I think you said social behavior, in theory, the same basic idea could be considered. The challenge is the motor systems we're learning is pretty complex, but it's probably the simplest of those models. So things like, we have done a little bit of work in language, but things especially like learning and social development, cognition, all those really complex brain functions tend to be not so much about one or two spots in the brain or nodes in a network. They're very complex networks. So that doesn't mean it's not possible, but it becomes much more challenging. And so there is some work in adult stroke, more directed to that type of question. Nothing yet in our field, and it will be challenging. Not impossible, but it'll be challenging.
A lot of interesting, challenging questions here for you today. And we have one from Facebook, and it's just going to take me a moment. I've got many screens on the go here this evening.
No problem.
One is this method currently in place for patients in Alberta? And do you have any implementation plans to expand this research to other provinces as well?
Sort of, yes. So the I mentioned the large trial that we're just finishing. It's called the SPORT trial, which we hope will give us a good answer about specific. It's designed to answer the question, does stimulation add benefit in addition to intensive therapy? We have to wait and see. We won't know till next year. If it does, it will be maybe ready for some early implementation. What's likely to happen sooner, we were just talking about it today actually, is the idea of combination of earlier intervention, which I didn't have time to talk about, and home-based therapy, other things that are coming out of national networks like Child Bright and Kids Brain Health. And these things are getting closer to implementation. And we were actually just talking today about how do we mobilize the knowledge from things like our trial and a few other trials that are going on to implement things like home-based, parent-driven early intervention therapy. So I think I'm only partially answering your question, but I think that's an example of something that's probably moving into the mainstream. Brainstem will be at least a step or two behind that. In fact, we probably need more positive trials, to be honest. Brain stimulation, you might know, is actually now Health Canada and FDA approved for major depression in adults. It's been an insured service now in Alberta for a couple of years. That took 15 years and 25 big trials. We won't need that many if it's actually working, because depression has kind of carved the way for it to become a more routine therapy. But we'll have to wait and see. Until then, the first part of your question, I think, was about it just being in Alberta. As I mentioned at the beginning, these things are still pretty much at the experimental stage. And so it has to be sort of within trials that we're funding and developing. BCI, which I talked about at the end, we are already looking at ways to build a network that will allow earlier implementation, but that's also still pretty early.
Yeah, that would be a fascinating argument as well, too. I've talked with a few organizations in the past about how we do not have a real drive for Canadian-driven technology when it comes to accessibility. So that could be a really fascinating future discussion as well, too. Daniela, you got the next question.
Well, hello.
There.
It was really good to hear you. Very nice presentation. I can tell that you're very passionate. Meet Vasilia. This is my son. He's
Hello.
18. And yeah, he's one of those children with quadri and very bright. So we did try most of it, what you were talking about, but not in Canada. For example, the magnetic, I remember taking him somewhere, whatever. And it is a shame that we don't have this kind of like accessible all the time, right? Even BCI, the brain interface thing, we did try that, but it was so robust. I'm hoping for that to come accessible for for everyone. Do you think that might happen?
Yes, thank you for your question. And I think we're learning from our past mistakes or challenges of the past, what it takes to move these things through from a research idea to a study to the real world. I think that BCI is, in some ways, it's earlier because there's almost no research going on in the field. We're trying to change that. I think it will change quickly. It's also completely safe, and it's only one step away from a lot of the other ideas and systems in place for other types of assistive technology. So, for example, we have an occupational therapist on our BCI team who has worked for a long time doing all sorts of other alternative communication methods and adaptive assistive technologies. And so she knows the system. And so we're already studying that about how do we just plug BCI into the system the same way you would if you were applying for an eye gaze system or a communication board or another piece of technology. We don't have to reinvent the wheel there. We just have to show that it works. And I'm making it sound easier than I'm sure it's going to be, but it's not, I think it's not that insurmountable. In fact, we have some efforts going on right now to start laying that groundwork to make it a potentially insurable service in, I'd like to say soon, and by soon I don't mean tomorrow, but I mean not 10 years like it seems to take for other things. And so I'm hopeful that it will become, and that we do have a national network that's growing around this concept, and so the ability to have access at more places in the country and have it insured or fundable, affordable. I'm hopeful that that'll start to happen in the near future.
Do you have any recommendations on your website how to make a home-based one from Amazon or stuff?
From Amazon, no. Yeah, and we're not quite there yet either. We are developing. We'd like to develop a sort of a support platform that would, if we had the resources, that would allow us to extend our reach, so to speak. So we are supporting multiple families in the home, as I mentioned. They're all currently local because building up to that required some in-person time to get to know the child and train and those things. We're not quite ready to just, we do have a package, like we do have it's actually not even that expensive, but we're not quite ready to, Amazon, like you said, to have Amazon deliver it to your house and take it out of the box and then get online with us and say, okay, plug this into this and here we go. And but that's not, that is one of our goals, and I think it's
it should be. I mean, I try everything. You imagine in 18 years what I have tried. I'm an engineer as well, so I plugged in possible and impossible together.
Right.
Don't laugh at me, because yeah, and it was a lot of failures. It was some of the
Right. So we
do. Yeah.
So our website that you asked about, if people are interested, has a lot of the fundamental and basic information. We can't offer that service yet, but there is more information there. And if you have other questions, you can reach us through that.
Okay. Can you just say your website again?
Yeah, I'll put it in the chat. It's BCI for kids, like number 4.
Thank you. Yes. Okay. Thank you.
I just put
Thank you so much.
You're welcome.
Keep working on this. This is important.
Thank you for your questions. And
Daniela's going to hold you to that too, as well.
Oh yeah.
Believe it.
And one more thing. Yeah, Vasily is as he is, but he does participate a lot.
That's great.
Okay, so that's not always the case that they don't. He is participating, but he can do more. I always say he can do more.
I understand.
Yeah. Thank you.
We have one last question, and then we are, which is, sorry, is there any evidence that conditions such as preeclampsia or HELP syndrome impact the risk of perinatal stroke?
There's good evidence that they don't. So there is about 6 or 7 very good studies, and we're just doing the largest one. It's almost finished, to try to look at all the possible conditions of pregnancy, labor, delivery, mom's health, baby's health, all those factors that might predict a perinatal stroke. And for the most part, there's very little association between the 2 factors that you mentioned, as well as a long list of other conditions of pregnancy that we've studied and others have studied. It comes down to what's probably, you'll recall I mentioned that most of the arterial strokes anyway are probably a placental problem. It turns out that's not even just one placental disease. There are many conditions the placenta can develop late in pregnancy, infection, inflammation, thrombosis, that's blood clots. There's a long list of conditions, most of which are, unless they're very severe, there's no symptoms. The baby seems fine. The mom doesn't feel anything. There's no way, the ultrasounds can't tell. And part of the problem is the placenta can even actually be very healthy, but if there's one spot that's has developed one of these problems, it only takes one clot, one tiny little clot, a few millimeters in size, to block the middle cerebral artery in the fetus. And so the placenta could be 98% healthy, and one little spot develops a problem that leads to a clot. And so I'm not a placental expert, and I can't tell you exactly the relationship between, but there is a bit of an association, say, between preeclampsia and placental disorders, but that has never borne out in the research that independently that preeclampsia or these other conditions carry any high risk or any ability to predict, a high risk pregnancy for stroke. I wish we knew that, but there's really no way to predict it.
Well, thank you so much, Dr. Kirton, for such an informative experience here this evening. And we are so thankful that you came to join us. And please, by all means, come back when you have some more advancements that you wish to share as well, too.